So today's lecture is about optical flow. So optical flow is probably something that you may have heard of before because it's a commonly used term. And it's also a huge area of research in computer vision. And so today, for better or for worse, it's mostly going to be kind of like me deriving stuff on paper. I'll show you a couple pictures, but fundamentally, you know, the output of optical flow and the process of an optical flow algorithm running is not really that exciting of a thing to look at. So mostly I want to concentrate on what are the big picture methods for how people estimate optical flow. And then, you know, all this to say that people have been working on this for so long that there are a couple of major ideas that I want to talk about today. But then to really get great optical flow requires a lot of nitpicky, careful attention to detail that, you know, many researchers have proposed little modifications here and there. I'll go over some of those, but to really get into it, you have to kind of dig down a little bit deeper than I'm going to be able to do in one overview lecture. But first of all, let's talk about what does optical flow mean, right? So remember that the theme of this chapter is what I would call dense correspondence, right? So for every pixel in image 1, we want to know where does that pixel go in image 2, right? So that's like saying that at every pixel xy, I have a vector, and that vector, let's call uv, that points to some other location in image 2, which is at point x plus u, y plus v. And the idea is that if this is image 1 and this is image 2, that image 2 at this location, the pixel intensities should be equal, right? That's like saying that this pixel, and we assume that this motion vector is kind of induced by underlying camera motion and possibly underlying object motion, right? So those are kind of the two things that can cause this apparent motion vector. And so in some sense, those two things are generally kind of tied up together in this motion vector. Now, oftentimes in optical flow, we think about, instead of these just being like two arbitrary images taken at different times, it's often instructive to think about these images as basically literally samples in time, for example, from a video sequence. And so another way of thinking about this problem is we could call this image I at time t, and this image I at time t plus 1. So there's basically like this interval of sampling. And then another way of saying this is that we could think about the image intensity as a function of space and time. So it's like saying that xy at time t, this whole pixel moves to this position in t plus 1, x plus u, y plus v, right? So in this sense, I've kind of taken out the I1, I2, and I've just said that there's this one three-dimensional quantity I that depends on both pixel location and time, okay? And so, again, just like for feature detection, most optical flow methods are defined or are kind of derived in a grayscale world, although everything that I can say can pretty easily be extended to colors. So here, I'm kind of assuming that there's a single channel of intensity, right, grayscale intensity, but if I wanted to, I could also assume that these were like 3 vectors of RGB, and I want those RGB vectors to be the same, right? So today I'm going to talk about the general problem where there really aren't any major constraints on U and V. In theory, you know, all things being equal, any pixel could go anywhere else. Now, we're going to talk about the stereo problem after the spring break, where things are a lot more constrained. It turns out that if I have 2 cameras that are basically rigidly mounted to like a bar, and I'm moving that array around, so they're taking basically 2 images of the same scene at exactly the same time, just slightly offset, in that case, there are some pretty severe constraints on where the correspondences can be. And we turn things from being a kind of a 2-dimensional problem, estimating UV, to estimating one parameter for each pixel, which is basically called the disparity. So we're going to talk all about that next week after, or not next week, the week after next, after spring break. So that constraint is called the epipolar geometry, and the problem is called stereo. Okay, so we'll get back to that in a while. So for right now, we're going to assume that we just are estimating this vector UV at every pixel, and that's the story. And so this here is kind of the key assumption that we make in optical flow. This is kind of called the brightness constancy assumption. Right? And this kind of makes sense. This is saying that fundamentally, if I move the camera, and if stuff moves in the scene, that colors on the surface of the object cannot change. Okay? Now that's, in the real world, not really always true, and we're going to talk about some kind of relaxations of this in a few minutes, but this is where we start from. And actually, this also kind of ties up a whole bunch of other assumptions. So like if you're a computer graphics person, you may have heard of like the Lambertian assumption. This basically says that things don't fundamentally change color depending on what direction you look at them from. In the real world, these colors may change a little bit, but the way to think about this is that we want to make this as close to this as possible. Okay, and so let's take so the very first optical flow algorithm. The first kind of formalization of how to solve this problem was by Horn and Schunk. And so Horn is like a very famous computer vision researcher. Make sure I spell Schunk right. And so this is often referred to as just HS. Okay. And so the idea is, what if we were to take this equation here and expand it as a Taylor series? Okay. Again, Taylor series basically saying that I've got a function that is, I want to estimate what this is, and I know it's close to this, right? So it's like I'm expanding this around u and v, where I assume that the motion vector is relatively small, right? So if I expand the Taylor series of the brightness constancy assumption equation, well, let me look back at this for just a second. So that's basically saying I'm going to have the derivative of x multiplied by this delta, the derivative of y multiplied by this delta, and the derivative of t multiplied by this delta, which is 1. So that's like saying that di dx times u plus di dy times v plus di dt times 1. That's the increment. The kind of constant term is basically saying that I get to, x plus u, y plus v, t plus 1 by taking what I had here and adding it to this. And so this is the brightness constancy assumption, and I can see that these two things are going to cancel. So what I get is basically something that involves the gradients of the image in both space and time. Okay. Another way to think about this is that fundamentally what I have is I have the gradient of I, right? This is like the vector with these two partial derivatives, dot with the flow vector equals this number. Okay? So basically at every pixel, I have this one constraint, right? This basically tells me that I know what the flow vector direction should be when it's projected onto. So this basically is telling me that I know, what the UV should be in the direction of the gradient, right? But what I have here is one equation in two unknowns, right? I have, U and V to estimate, and I only have this single equation in U and V to get my optical flow. So basically this means that I have an under-constrained system, right? So this is only one equation in two unknowns. And so that means I need more constraints. So, that's like saying that the optical, the brightness constancy assumption that colors don't change is not enough for me to estimate the entire flow, right? And so, one way to think about why that's true is that if you imagine that I had, a flat block here and a flat block here, I could have the flow vectors pointing any which way between any of these flat pixels and any of these flat pixels. All those would satisfy the brightness constancy assumption, but clearly some of those flows are better than others, right? I want a flow where the motion vectors are not like crazy, mismatched, right? So the intuition, it's kind of similar to the intuition that we had for the matting problem, is that pixels that are near each other should have similar flow vectors, right? So we're going to kind of impose that assumption, and that again makes sense, because if you think about it, that's generally true almost everywhere in the image. So if I'm moving, suppose I've got no moving objects in the scene, I just move the camera. As I move the camera, the motion vectors of all the points in the background are kind of going to move smoothly, right? So I'm not going to get, motion vectors that totally disagree with each other for camera motion. And again, even if I have object motion, so say I've got a person in the foreground who is kind of moving simultaneously, so in that case, most of the flow vectors are, again, going to have the smoothness assumption, right? All the vectors on the moving person will kind of be roughly the same. They'll be smooth, and all the vectors in the background will be smooth. You do have some issues where there's the interface between the person and the background. In that case, a pixel on the person that is right next to a pixel on the background may have very different flow vectors, right? And so the one case where this doesn't hold, one example is basically foreground, background boundaries, okay? But generally, we can be safe in imposing some sort of a smoothness assumption everywhere, okay? And so that means that what is our other constraint going to look like? Well, one thing that we might want to do is imposing smoothness. We might want to minimize something like this. Right? So this is kind of like saying, again, what I'm estimating for optical flow is for every pixel I've got a UV direction, right? So it's kind of like saying I have it's like saying I have a vector field over the domain of the image. And this is saying that, the U values, this is like saying what is the change in the U values in X and the change in the U values in Y, and the same here. So, this idea is I want this to be small. That's like saying that I can't get any big changes, or I shouldn't get very many big changes in the flow vectors, okay? And so if I put this all together, the Horn-Schunck method is basically to minimize basically the following thing. I have a cost function that looks like over all the pixels in the image, I want to take this number, which is related to how well the pixels fit the brightness constancy assumption. And then I want to add some factor times this number, so one way to think about this is that this is like saying that I want to minimize something that depends on the data and something that depends on the smoothness. And what I'm doing here is I've got this factor lambda that kind of trades off these things, right? If lambda was huge, then basically that would be like saying, well, above all else, I want the flow field to be smooth. And so in that case, if this term didn't play a role at all, I basically have a constant flow field. That would be the smoothest thing I could get. If I make this lambda 0, then I have the chance of getting things that agree with the brightness constancy assumption but aren't smooth at all. So what I want to do is I kind of want to choose my lambda to balance these two properties. And so this kind of formulation, this kind of thing is often called a regularizer, right? It kind of means that I don't have enough constraints, so in the absence of constraints, I put this kind of smoothness term on, and I have to decide how do I tune my lambda to make the field smooth, right? And so again, it's kind of a black art to how do I choose this lambda. This lambda may change over the course of iterations that I use to solve the problem, but this is the basic idea, okay? So let me pause and ask, are there any questions about the setup? Yeah?
Isn't the data term 0 here?
Well, I mean, ideally the data term is 0, but in practice, when I have real images, it's not going to be exactly 0, right? I mean, ideally, we want this to be exactly 0, but it's not going to be, right? So when I calculate my best U and V, the best I can hope for is that this is going to be small, right? Because one of the reasons is that real images deviate from the brightness constancy assumption, right? So things just due to pixel noise, non-Lambertian surfaces, lighting changes, all that stuff will contribute to non-ideal conditions. Yep.
I just want I think you made a slight error there.
Error?
I think you
you have to interchange the partial of V with the Y there, right?
What I do here?
It's like DI, you have DI, DV.
Oh, yes, you're right. Wait. You're right. This has to be, this is bad, right?
Yeah,
this needs to be Y.
Yeah.
That's it, right?
But no,
In the data term as well.
in the data term, you have.
Yes.
Yeah. That's all.
Sorry. Yeah, good catch.
It's funny too because I copied it down correctly. But
Yeah, this stuff, unfortunately there's all this kind of like U's and V's, X's, Y's, and so my apologies. And so this is the fundamental idea. I mean, this idea was presented back in the early 80s, right? And so all this stuff can basically be estimated from the image, right? These things here are just gradients of the image. This here is also like a gradient, but just taken in the time direction. So I can compute all this stuff from, for example, just finite differences of pixels. These things here, right? Again, since in the real world I'm estimating a flow field that is discrete, right? So again, these are going to be like finite differences from the U and V fields. So there's really nothing here that I can't do in a discrete world, right? And in the book, I kind of mentioned how you would kind of set up the discrete versions of these quantities, right? So, fundamentally what this would come down to is solving some big linear system over all the possible UV values, right? So you'd have a big matrix that would have lots of values from the two original images. Your unknowns would be all the UV vectors, and you have a right-hand side that would come from probably this stuff, and then you'd solve that linear system, okay? So there are some good things and some bad things about this. One is that the nice thing about having a regularizing term like this means that, without getting too mathematical, the closest way I can say it is it kind of reminds you, when you look at how it's actually solved, of a kind of a Poisson-like equation, in the sense that this is something that will do a good job of filling in things smoothly. This is like a diffusion equation kind of system. It's basically saying that even when regions are flat, if I have good constraints for how stuff move around the region, those constraints will kind of force all the stuff in the middle where I may not have very solid constraints to kind of follow along, right? So this means that I will get a very nice, smooth flow field. One of the immediate problems, though, is that this expansion, this Taylor series expansion, remember from your calculus, only is really valid when the increment, this UV step, is very small, right? So there's this underlying assumption that basically says this will only work when the motion vector itself is very small to begin with, which means that the two images have to look almost exactly the same to begin with. We know that that's not going to really happen in most flow problems, right? So, for example, for this to work, you really would want, for example, U and V to be less than a pixel, right? And of course, if there's less than a pixel of motion, then you've got basically no motion at all. So one way that we can get around this is to make the method kind of hierarchical. So and then this kind of idea generally applies to not just the Horn-Schunck algorithm, but just general optical flow algorithms. The idea is kind of remember how we talked about making a pyramid for the image, right? So we basically said that I could take my big images and I could make, for example, a Gaussian or a Laplacian pyramid where I make smaller and smaller versions of these images, right? And so the idea behind a hierarchical optical flow method is to say, okay, I make a pyramid of images, and then I first compute optical flow between the two images at the lowest level, right? Because these are really tiny, blocky images, and at this point, the flow vectors are all really going to be, you basically want to bring down your pyramid to the level that your flow vectors are going to be on the order of a pixel, right? Now, again, if I start with a 640 by 480 image, and I bring this down to like a, 16 by 12 image, well then, yes, I could probably have some pretty good faith that the pixel vectors are not going to be more than 1 pixel in that tiny, tiny image, right? And so the idea is, okay, well, I compute the flow here, right? And then I kind of could say, okay, well, to get an estimate of the flow from here, I could double all of my magnitudes of those flow vectors and use that kind of as an initial condition for the next optical flow problem. Part of the trick, though, is that, again, I can't do that directly in the sense that even if I was to say, okay, well, now I have all these UVs that are on the order of 1, at this level they're all on the order of 2, at that point, again, the Taylor series expansion for vectors of that size is not valid, right? So what you typically do is I say, okay, I have a model for how this thing, how the pixels here map to the pixels here. And so what I can do is the first thing I do before I estimate the flow at this level is I warp all the pixels from here to a new image here. It's like saying, okay, push those vectors along their flow, or push those pixels along their flow directions to make a new image, right? So the idea is that this image should be pretty similar to this image. And then I compute the flow between this guy and this guy. So it's like saying, okay, when I push the vectors at the highest level, I get an image that looks pretty good at the low level, but when I upsample it, now I find that actually, I'm going to be a little bit off from that assumption, right? So now the hope is that at the second level, the error between this and this warped image are going to be basically, again, on the order of 1 pixel at the next level, right? So I keep on doing this step of, estimating flow, warping one image to another, and then estimating flow at the next higher level. So at every step, I'm always estimating flow vectors that are on the order of a pixel, but those kind of composite warps are going to add up to flow vectors that could be, theoretically much larger than a pixel, right? So basically, that's the general idea. That the algorithm that I put here in the book gives you the more specific details.
So to summarize.
Yes.
So you estimate the flow, and then you warp it, and then you upscale it, and then you compare it with the next level.
Right. Let me try and be a little bit more concrete about this, just so that I'm clear. So basically, the algorithm. I know I have a kind of a tendency to be hand waving in these lectures. So basically, the idea is, create pyramid for each image. And so let's call these pyramids basically I1 sub I and I2 sub I, where basically I indexes the level of the pyramid. Okay? And so the idea being that I1 sub 1 and I2 sub 1 are basically the finest level, like the original image, and I1 sub n and I2 sub n are the coarsest level. And these are going to be basically the blockiest images. And so the idea is that, okay, so let's suppose that I start with these two guys, right? So now I'm going to basically estimate. So this is going to be looking something like for j equals, n, I'm going to kind of start at the lowest level, the coarsest level. I'm going to work my way back up to the highest level, right? So I'm going to estimate the flow between I1 sub j and I2 sub j, right? And this should basically be on the order of a pixel at that level, more or less. Okay? So this is going to kind of give me a flow field at level j. Okay? And then what I want to do is I want to figure out at the next highest level what should be the flow field that I start with. And so what I'm going to do now is construct the flow field at level j minus 1. So how do I do that? Basically, that's like saying I would take this is where the math gets a little bit messy. What I do is I'd say something like, okay, the UV at level j minus 1 is going to be like 2 times the UV flow field at level J plus 4 times whatever the flow field was at J plus 1, all the way to, 2 to the whatever, I'm going to put a box here, times the flow field at the coarsest level, right? So basically that's like saying that to build up where I should be at the next level, I have to kind of concatenate all the flow fields that I had below me, and I have to multiply those by the corresponding power of 2, because these images are all, proportionally smaller by a power of 2, okay? And then I'm going to warp okay, I guess I drew my picture a little bit wrongly here, but I'm going to warp I2 at level J minus 1 to some new image using the using this flow field. So I guess I drew this picture wrong in the sense that I'm not warping this image, I'm warping this image. So I'm going to redraw this in a second. Right, so basically this is saying, okay, what I'm going to do is I'm going to push the image 2 intensities over by the estimated flow vectors so that now I don't expect there to be a big difference between image 1 and image 2, except for maybe another pixel offset at the current level that I'm at. And then basically I kind of set my working level to J minus 1, and then I would kind of iterate to go back here. So the kind of thing is I'm basically continuing to keep on estimating flow fields at the finer and finer levels of the image, and every time I kind of add on, okay, so then what should the warp look like based on everything that I've learned so far, and then I'm adding the finest little increment, the little adjustment at the top layer, until I work my way all the way back up to the fine level layer, right? So that's the idea. And so let me kind of redraw my picture. I realize I did this wrong. So the idea is that I have the highest level images. So these are basically like the N level images. And these are like the 1 level images, right? So this would be my UV flow at level 1. Level N, sorry. Actually, I marked this wrong. This is 1, this is N. Right. So this is my UV flow at level N. And so that's like saying, okay, well, now what I want to do is I want to push this image over by using twice the estimated flow field at the bottom here, so that these pixels move over to roughly where they should be, right? And then I estimate the flow between these two guys. And this is what gives me kind of the next flow level. And then this guy, I'm going to warp over here using both this thing and this thing. These both go into estimating this warp, right? And then I estimate the flow between these things, right? So basically I keep on kind of bootstrapping my way up to the top.
So I'm having a hard time following this flow real quick. So you're estimating the warp between the blockiest images, and then you're using that flow to warp
The next
level target image, like, or
yes.
a second image, right?
Right, right.
So you use that flow to warp that one, and then you compare the first image, T at T, to that new warped T plus 1 image.
Right.
Yeah, so you use the estimate down there, and then use that to work the 1 level above.
Right.
Use that to estimate the UV again, and then use that to work the 1 level above.
Interesting.
Right.
So why are we
warping?
why are we warping the image that? I mean, I guess in my mind it would make more sense if we were using that to warp the left-hand image.
Oh, I see what you're saying. So, I mean, the question is, why would we not warp the left-hand image? And in theory, you can do that too, right? I mean, it doesn't really matter which one you warp as long as you are consistent about it in some sense, right?
Okay.
So, I mean, you could make a hierarchical implementation where you kept on changing image 1 instead of changing image 2. You just have to keep it straight.
Okay.
Yeah.
So then the final vectors that we come up with is the result of warping the level 1 image, and then calculating as well, and then adding that on to the result.
Right. So the final flow vector is going to be basically like saying, okay, suppose I have like 4 levels of the pyramid. It's going to be like saying, okay, I'm going to take 4 times the vector, or it's like saying I take 16 times the coarsest flow vectors plus 8 times the next coarsest plus 4 times plus 2 times plus the finest increment, right? So yeah, it's going to be a concatenation of a bunch of flow fields, right? So, yeah, I know this is a little bit confusing the first time you see it. Other questions, comments?
It's starting to make a little.
Yeah.
I mean, I don't understand how warping the T1 in, but I guess it doesn't really matter.
It doesn't really matter. I mean, the main thing is that if you don't do the warping, your flow vectors are going to be too far away for this Horn-Schunck method to get a good estimate, basically, right? I need to make sure that the 2 images are almost directly comparable, right?
Well, the reason why I'm confused is because if we're going to be estimating the flow from left to right, it's not the same thing as estimating the flow from right to left.
That's a good point. So the left to right flow and the right to left flow are not always necessarily the same. In theory, they are opposites of each other, right? So I mean, in theory, if I were to look at the optical flow from here to here, all my flow vectors would be negative, right?
Right.
Theoretically. But what causes that to screw up, and I'm going to talk about this towards the end of class, are things like occlusions and other issues. So let me talk about that a little bit later, right? But in theory, they're reversible, right?
I guess what I'm trying to figure out, though, is how I can see how if we're calculating the UVs from the left to the right-hand side image, then applying those to warp the next level left-hand image because they're in that direction. Oh, never mind. So, okay, yes. All right, so this is what we're doing. It's just that because of the way that you drew it, I got a little confused about which image is which. Yes.
Okay.
No.
No?
Damn.
Would you?
Because I was on the warp here.
Would you be warping in the opposite direction, like you're warping? I think that's what he's asking.
Yes.
I guess that's what I'm.
So the question is, which way am I warping?
So when you warp, like when you reposition the pixels or whatever using that UV vector,
Yep.
would you move it in the UV direction or
the negative UV direction?
Negative UV direction, I guess.
Yeah.
Right, I see what you're saying. Which direction do you move?
Because the way that you've drawn it here, I would actually switch the UV n-1 and the word warp.
Yeah, okay, so let's think about this. So this is a good question, and now you're making me doubt my own sanity. So let's think about this at 2 levels, okay? So we have the high level and the low level. I remember thinking about this at the time and being pretty sure I got it right, but let me just, hopefully this is not going to be embarrassing for me. Okay, so let's suppose that, let's suppose that here I have like this vector 2, 3, and I estimated that it went to 5, 8 or something like that. Okay, so my estimated flow vector here is going to be. Actually, this is a bad example because this is too big of a thing. So maybe it should be something like 2.5 and 3.2. Okay, so my estimated UV is going to be 0.5 and 0.2 for this vector. Okay, for this point. All right, now I bring things up to here, right? So this point will become 4, 6, and this point will become 5, 6.4. Okay. So the idea is that I'm saying that these things are comparable.
And then you have subpoints that you're going to be new pixels that you're going to be.
I'm going to have pixels that I'm now going to newly estimate this. All right, so let's think about this. So you're saying that I should warp this image back. I should float.
Either you warp that one back, or you
I warp this
forward,
one. Right.
Using the UVs, because I'm not necessarily sure that well, I guess the flow could be. I'm just basically confused about the positive and negative relationship between UV and these pixels.
Yeah.
And the warping. That's all.
Yeah.
I was curious to see if you would warp the original image forward, or if you could get the same result by warping the second image T plus 1 backwards.
Right.
Using the negative UV.
Yeah, I think in principle, I think they would be
Because you're trying to bring them closer together.
You're trying to bring them closer together,
If
right?
you were to warp the T plus 1 image using UV, you would actually warp it further away from.
Yeah. So you're saying that I want to warp this to, I want to bring this back to 4.5, 6.2,
Exactly.
and then have the error be on the order of a pixel, as opposed to going this way.
Exactly.
That definitely makes sense.
Okay. So if you do the warp into that image, I can understand that, but maybe
Right.
you do it in the negative direction, or just use UV positive to warp the left.
I think you're right, and that makes me think that I have a typo here. So let me go back and revisit this. But I think that you're right. The intuition is correct, right? I want to make this pixel as similar as possible to this pixel, right? And so that makes sense that I want to reverse the flow. Or conversely, I want to push this pixel forward to 4.5 to 6.2 here, and then estimate the flow between these things. Okay. Yes. I think you're right. I need to go back and kind of convince myself, but I think that you're right. Yeah, I kind of was worried about while I was writing it down, actually, that I was going the wrong way. But yes. Okay, good call. All right.
Are you taking the pixel 4.5 or 5 using twice UV here?
Well, yeah, I guess that's the other thing, is that I need to multiply this by 2, right? So really I should be warping with the double vector. So I should be moving something by 1, 0.4, right?
Yeah, and when you warp that.
So then this would move to 5, 6.4.
Right, and then you estimate the flow for all the pixels around.
Yeah. I guess that makes sense, right? So that's like saying I want to push this over to be exactly this point, right? And then I have some error in that estimate. Yeah, that makes a lot of sense. Okay. So it seems like the right thing to do is to basically either push image 1 forward or push image 2 back, right?
And I think in principle they should be equivalent.
In principle, they should be the same,
Yes.
right? But I think that actually in practice, it makes more sense to push image 1 forward, because that's really what your model is, right? You're modeling things as pushing image 1 forward. So it would be better to push image 1 forward to this, and then estimate the flow here. Yeah. So I think I just basically have image 1 and image 2 reversed in my derivation. Okay.
So what you had in the beginning was
Yes.
What I had in the beginning was correct, and that's what kind of, and that was what makes sense to me in the first place. So okay, all right. Well, I'm glad we had this little talk. Okay, so all right. So just to kind of give you a sense of, so what do you get when you finish with an optical flow algorithm? Right. So here's a couple examples of 2 images. In this case, I moved the camera. There was no actual object motion, but this is the kind of result that you get out of a flow algorithm, where basically at every point I can visualize the UV direction. And so in MATLAB, for example, this would be called a quiver plot, where you basically take an arrow and you put it on top of every point. Just FYI, so part of the homework asks you to make such plots for a few canned optical flow algorithms. And so in this case, I kind of made this picture with a combination of MATLAB, and then I went in and probably touched up the arrows a little bit so they were more visible. You can do this all in MATLAB, but just a word to the wise that what comes right out of Quiver may not be very easy to visualize. So you probably want to make your own little algorithm that decides how far apart you want the arrows to be spaced and how thick you want them to be, just so you can see what's going on better. But in this case, again, you can see that from going from image 1 to image 2 is this kind of clockwise twisting motion, and that's captured by the flow field, even in cases where there's nothing really to grab onto to estimate, right? So for example, there's a whole big flat background here that I really don't have anything to grab onto feature-wise to estimate flow vectors, but the fact that the Horn-Schunck algorithm has this nice smoothness property forces all the other vectors to kind of follow along with what the rest of the pixels are doing, right? So that's why things are good, is I can still get a good estimate of the flow vectors everywhere, even if I don't have a lot of image texture nearby to grab onto. Okay, so that's one kind of key idea for optical flow. The other key idea is kind of based on feature tracking, and so that's called the Lucaskanade method. So one way to think about that is that the main idea is I could say, okay, well, let's suppose that I want to kind of think about flow as a process of matching local pixels, right? So one thing about the Horn-Schunck method is it wasn't really clear how nearby pixels were related to each other except via the smoothness term. Another thing that I could do, which makes a lot of sense, kind of in the context of feature matching, would be to say, okay, I'm going to draw a small box around each point, and I'm going to try and find the best small box over here, right? So it's kind of like saying I want to move this whole box of pixels from there to there, okay? And so what I could do is I could make an energy term that basically looked like this, where I'm saying that for every point xy, I draw a window or a box around xy. So this could either be a box filter in 2D, or it could be like a Gaussian like we were using for SIFT and stuff like that, where I'm basically weighting the pixels unevenly. And then what I do is I say within that region, I want to look at the pixels. Actually, I should have written this in. I want to look at the pixels here and the pixels over here, and I want to minimize this energy function, right? That's like saying that over the window, I want this number to be as small as possible, right? That's like saying, kind of again, I'm using the brightness constancy assumption, but I'm making kind of the implicit assumption that locally the UV vectors inside that window are all the same for that, for that local neighborhood. Okay. And so if I were to write out what the implications are for kind of minimizing this kind of function, what I would get would be something that would look very familiar from our feature matching part. So basically what I would get would be something that looks like the sum. I'm going to kind of take the window part out of it, but I'm going to get something that looks like this. The sum is over the window, right? So this is kind of like if I'm making a box window, then I'm kind of simplifying this slightly. So this thing would multiply the flow vector, and then what I would have over here would be a vector that would look like basically the sum over the window of di dx, di dt, and di dy, di dt. Right? And so if you look at this is exactly the Harris matrix that we derived last time for features.
So
question?
You do this for all pixels in the image or all features?
I'm doing this for all pixels in the image. Right, so that's a good point. So this matrix last time came up in the context of finding features, right? And so what we found out was that for a feature to be good, the eigenvalues of this matrix had to be nice and large, right? If the eigenvalues weren't large, that would mean that either the patch was flat or I had the aperture problem where there was an edge and I couldn't estimate the motion, right? And so that's exactly the problem with this method, is that the assumption is that there's enough texture inside the block to make this motion vector accurately measurable, right? And so that's the drawback of this method, is saying, okay, for this to work at every pixel, I may need to choose my boxes to be relatively large, right? And then if I choose my boxes to be relatively large, the assumption that the same UV holds for all the pixels in the block may be compromised, right? And so that's exactly the trade-off, is that, this is good to use some local image information, but it may not be reliable if your boxes are too small, okay? And so the nice thing about this is that I could compute the flow vector at a given point somewhat independently of the rest, right? So Horn-Schunck has the advantage of coupling all the pixels together into one big thing. So that's the kind of difference. Is the Horn-Schunck is global and Lucaskanade is very local, right? And so the best optical flow algorithms leverage both of these ideas, right? So what you actually see in practice is that you take a cost function term that looks like this and a cost function term that looks like Horn-Schunck, and you weight them together, and that's how you obtain a good flow field, right? So what we're going to talk about next basically are some refinements and extensions to the basic optical flow algorithms we've talked so far that kind of combine best practices from all of the stuff that we've said. Okay, so let me talk about kind of refinements and extensions. And so I think it's fair to say that if you were to just take Horn-Schunck like I wrote it, or Lucaskanade like I wrote it, and expect to get great optical flow fields, those won't give you good optical flow fields in general for real scenes at all. You have to do a lot of extra little work to make sure your optical flow field is good. Okay, so one thing basically I have still two key concepts for any flow algorithm, right? One has to do with the data term. This says how well do the pixels fit the brightness constancy assumption. The other one has to do with some sort of a smoothness or regularization term that says how similar should nearby flow vectors be, right? So any optical flow algorithm kind of has two things like that. So one is you could, instead of using a brightness assumption, you could have a kind of a general version that says, instead of having to have the pixels exactly the same intensity or color, instead you could say that I expect that the gradient at this point matches the gradient at that point. And so this, for example, could help with cases where, if there are some slight illumination changes in the scene between the two pictures, the main thing I want to get across is that the edges in those regions should basically be the same, right? So I don't necessarily have to get exactly the colors to match, but I need the differences in colors to match, right? So in some sense, it's kind of like what we were doing with the Poisson image editing, right? We were forcing the gradients inside the target region to match up with those of the source, right? So this, you can basically either replace the data term with this entirely, or you could say, okay, my data term looks like, some difference between I could say I've got something that differs in terms of brightness, and then I have something that differs in terms of gradient. Right? So I could kind of trade off and say, okay, I want both of these things to be true, and depending on how serious I am, maybe I would make this gamma stronger or less strong, right? So, I mean, this is definitely a common thing to want to do. Or, you can kind of do a combining Horn-Schunck and Lucaskanade, right? So what I could kind of do is I could say that my cost function term is something like, I use the local Lucaskanade term for the data part, and then I have the, Horn-Schunck term for smoothness. And so it's kind of like saying I kind of take the best part of each of the two algorithms, right? Because Horn-Schunck is good for enforcing general smoothness, and Lucaskanade is good for using kind of spatial, local spatial stuff, right? And so this was the seed of an algorithm by Brun et al. That turned out to perform really well. And kind of similarly, this idea was an algorithm by Brox et al. So for a while, these kinds of modifications made much more reliable optical flow algorithms, right? So if you look in the back of the book where I'm talking to visual effects people, they used both of these types of algorithms for quite a while to do their optical flow. Another thing that you can do to make things a little better is, so the smoothness assumption is valid almost everywhere, right? That is, in the middles of foreground objects, in the middle of background objects, you want to enforce that kind of smoothness. But you don't want to enforce it across foreground to background boundaries, okay? And so, one thing that you can kind of do to modify the smoothness assumption is to say, okay, I don't want to smudge the optical flow across edges that could represent depth discontinuities, right? And so oftentimes a clue about whether something is, closer to the camera than another point is that there's a difference in color, right? So oftentimes color edges in the image are kind of proxies for possible depth edges in the scene. And so kind of the way to think about it is, I don't want to have consistency of flow vectors across the edge, right? That means that if I smooth stuff across the edge, I may be forcing these two vectors to be the same when they shouldn't be. But I can smooth down the edge, right? So kind of to draw this, that's like saying that suppose I have a strong edge in the image, I don't want to have this pixel and this pixel necessarily have the same motion vector, but I'm perfectly okay with having this pixel and this pixel have the same motion vector because they're part of the same area. And so basically the idea is don't smooth across strong edges. Part of the reason being these could be depth discontinuities, right? And so here's kind of a picture of a goat. So the idea here is what you can do is you can apply what's called an anisotropic diffusion tensor, which is a fancy way of saying you can estimate for every point in the image an ellipse that kind of tells me what direction the edge is pointing and how strong it is, right? So for example, here, along the bars of this cage, I've got strong ellipses that kind of are narrow and go up and down along with this cage. When I've got a flat region, like here, basically I get, a circle, which tells me that there's really no strong edges in that area. And you can kind of see in other regions of the image, basically, these ellipses kind of follow along with how edgy the image is at that point, right? And so the idea is that what I would do is so if I compute this ellipse for each region, this is kind of like saying in what region of the pixel do I want the vectors to be smooth, right? So here, this would be like saying, okay, along the bars of the thing, I want the values inside this ellipse to be roughly the same, but I don't want to go outside the ellipse because those may be different values, right? So this kind of idea, it's a simple incorporation of not smoothing across edges, again, suddenly makes your flow fields a lot better because now you can tolerate differences across edges that otherwise with Horn Chunk you would just like smooth right over, right? So this is a very common thing to do instead of just kind of regular flows. Another thing that you see, and this is something that is a general issue in lots of computer vision problems and estimation problems in general, is what I would call the issue of making a robust cost function. And so what that means is that, when I'm solving so kind of what I have in the data term, for example, is I have the difference between this number and this number. And I'm squaring it, right? So this is basically saying, okay, when I have a very large error, if I square that number, I get a huge number, right? And that can really contribute a lot to my cost, right? And in this way, you find out that points that are really outliers, like if I happen to have a really bad UV vector estimate at that point, that could really contribute over much to the cost function. It can throw off the whole estimation problem and prevent the estimates from being good, right? So kind of the way to visualize this is that as a function of error, my cost function climbs up very quickly, right? So that looks like a parabola that climbs up very steeply. And that's not good for resistance to errors, right? Because if I have a bad error, I could be way out here and I could have some huge number for my cost function that's going to throw off however good the rest of my points could be. This guy is going to pull things away. And so, that's a big problem in general estimation, is how do you prevent outliers from corrupting your estimate? One way that you can do it is by not letting points that have high error just blow away your cost function, right? So one thing that you could do is basically, instead of having a cost function that grows quadratically, you could have one that grows linearly, right? That's a little bit better. Or even better, you could have something that kind of looks linear and then kind of tapers off so that you can't grow arbitrarily large, right? In this way, the influence of really bad outliers is mitigated, okay? And that turns out to be really important for designing good algorithms. Question?
Can you just ransack it?
Couldn't you just ransack it? Well, ransack is a way of dealing with outliers for certain kinds of problems, but so it's not really relevant here because the fundamental assumption about ransack is that all the points are related by the same underlying parameters you're trying to estimate, right? Whereas here, I could have a different UV vector for every pixel, right? So the key that you was missing to use ransack here is consistency of the thing that I'm trying to estimate, right? That's the idea. I mean, ransack is a way of dealing with these kinds of outliers in problems where you have kind of a single parameter. So for example, ransack would be good for the thing I'm going to talk about next, which is basically, supposing that I decompose the image into layers, and I said, okay, within each layer, model the flow as, say, a projective transformation like we talked about last time. Then there's only a few parameters to estimate, and then I could tolerate outliers if I say, okay, I got everyone in this foreground region, I'm only trying to estimate these 4 numbers or 8 numbers. So I can only then I could do ransack within each layer to estimate the flow vector. Right. That kind of idea would work then. And so here's kind of a picture of what these different robust cost functions might look like, right? So generally it's a good idea not to use a square function in either the data term or the smoothest term. So what you would do is instead of writing it like this, you would instead have a term that looks like some row that operates on this difference. Right? So this row is going to be one of these robust cost functions that isn't just the square of something, it kind of mitigates big errors, right? So that robustness turns out to be very important. Okay, so something else that was mentioned earlier was, in theory, right, isn't the flow field reversible, right? So I mean, if I have the flow from image 1 to image 2, if I were to compute the flow vectors from image 2 to image 1, shouldn't I basically get the negatives of those flow vectors? Well, the problem is that doesn't always work very well. And so one big reason why that doesn't work is what are called occlusions. So occlusions come from a situation like this, where you have pixels that are visible in one image but not in the other image, right? So supposing that I had this set up here, in this case, in image 1 I can see the corner of the painting, in image 2 it's occluded by the head of the sky. On the other hand, in image 1 the guy is standing in front of the corner of the window, but here the window is revealed as you see a different camera perspective, right? So the problem is that there's no position in image 2 where pixel A will have a good match, right? You just don't know what that number is. And in the same way, there's no good match for pixel B over back in image 1, right? So if you force yourself in your flow algorithm to have to match every pixel in one image to the other image, you're going to have a bad time because you're going to have occlusions, right? And so depending on the situation, things may not be so bad. Like, so if I have a pair of images from a video camera that are split apart by a 30th of a second, then how bad could things get? Probably not super bad, right? But if I have 2 images, for example, from a stereo camera, where the 2 cameras are a meter apart, looking at this image at the same time, well then maybe I could have some serious occlusions where there's like these rinds around the foreground objects similar with what we were talking about for matting and inpainting, right? So when I see behind an object, you know, I have to figure out, well, I don't have the correspondence to put those pixels there, right? So I'm going to talk more, I think, about occlusions when I talk about stereo correspondence, but at the very least, you could use an optical flow algorithm that tries to check for occlusions and mitigate them, right? And so the easiest way to think about that is if I have a candidate optical flow field, so say I'm looking at this white pixel, right, and I estimate that the motion vector is pointing towards this black pixel over here. What I could do is, okay, now I could compute the flow from image 2 to image 1, and I can check to see, well, where is the flow vector for this black pixel pointing? Is it pointing back to the position of the white pixel in image 1, or is it pointing somewhere else, right? So if life is good and things are symmetric, then the white pixel in image 1 should be the same as the gray pixel in image 1 that's implied by going forward and back along the estimated flow. If it's not, then I should throw out one of these flow vectors and not even try to consider the flow, right? So kind of, you know, if you look back at this picture, you can see that, you know, there are kind of two kinds of occlusions. One is when I've only got the pixel visible in image 1, and one is when I've only got the pixel visible in image 2. And so you can kind of distinguish what case you're in by looking at how good the data term is for each of these vectors, right? So for example, if I've got an image point that is visible in image, how do I want to say this? So basically, I can examine how good the data term is and see, you know, whether I'm occluded in image 1 or occluded in image 2. If either of these vectors points in the wrong direction, this is kind of called, sometimes it's called cross-checking or left-right checking. If I find that I'm in that case, I can kind of throw that flow vector out. So I can do cross-check or left-right checking to detect occluded points. And then, you know, the most I'm going to say about that for the moment is just not to use those points, right? We're going to say more in stereo about how that works. But basically, you know, there's not that much you can do when you've got occlusions, right? There just isn't a point that you could assign that you would be able to reliably estimate. Another modification is called layered flow. And so the idea here is pretty straightforward, right? So you imagine that, again, I talked about the person moving in front of the background. What you could kind of say is, okay, so if I've got, you know, this person moving in front of the background, so the person and the background are going to appear to apparently move at different rates in terms of measured on the image plane, right? So stuff that's closer to the camera will generally move faster than stuff that's further away from the camera, right? And so what I could do is I could say, okay, I'm going to try to segment out this foreground, and I'm going to call this background layer 1 and this foreground layer 2, and then within each layer, I'm going to basically, I could maybe get away with estimating a parametric transformation, right? So for example, I could say, okay, I'm going to estimate a projective transformation for layer 1, and I'm going to estimate a projective transformation for layer 2, right? So there's not one good transformation that applies to the whole image, but if I am able to split the image apart into good boundaries, so in some sense this is kind of like the matting or the foreground segmentation problem, right? So if I can accurately segment the foreground pieces, then I could maybe say, okay, I'm going to assign each of you a relatively simple motion, and then I can compute the whole optical flow field by putting these motions, you know, back together in the appropriate ordering, right? Or if I don't want to be really precise about forcing all these guys to have the same consistent motion vectors, I could have something where I have what's called like smoothness in layers, where I say, again, instead of just doing the anisotropic thing where I compute what direction I want to smooth every pixel, I could say, okay, I want everything within a given layer to be smooth, right? And I don't have any sort of smoothness assumption across layers. So sometimes you see this thing called smoothness in layers. And so, you know, that's another possibility for again, there's a little bit of an extra step here that may not be really worth it because, estimating the layers is already a kind of tricky thing, as we saw from matting, right? It's not so easy necessarily to really accurately draw a tight outline around the foreground. And as you saw in Chapter 2, there's lots of cases where for different kinds of objects in the foreground, there is no nice hard segmentation in the first place that would be a good layer. So when you see this applied to real images, you often see it in the context of things like cars and trees and stuff like that, where you can draw a nice hard boundary around the layers. Couple final thoughts. Another idea that you may see around is kind of what I would call large displacement flow. Right, and so the assumption that we made with this hierarchical method was that, at every level of the pyramid, my flow is relatively small, right? And that, for example, suppose that I'm, like waving like this. My hand is small, the motion of my hand is kind of small relative to the size of the thing that's moving, right? But imagine now that I'm playing volleyball, right? So now I'm moving my hand really fast, right? So if I were to look at the pyramid images of fast motion of a small object, so for example, let's suppose that I'm, playing volleyball, right? And so here's the ball in one image, and here's the ball over here. Well, if I were to take this down to the smallest level of the pyramid, this ball is so small that I probably wouldn't even see it in these two images, right? Because it's maybe only a few pixels wide, right? So the problem occurs when I have, I'm mixing up my things. What I want to say is I have a few pixels here, but this vector is many pixels. Because I know that to estimate motions that are many, many pixels long, I have to have something along the lines of this hierarchical method where I build that long motion vector out of a bunch of smaller motion vectors that I saw at lower levels of the pyramid. For something like this, that object is not even going to become visible until I kind of get to almost the finest level of the pyramid, and by that time it's too late. I don't have any big motion vectors that I can add to that point, right? And so that's a problem for really like fast-moving video, for example. And so one idea that you may see is called sift flow, which is kind of a clever idea, basically saying that I can replace the brightness constancy assumption by saying that I want the sift descriptor at a pixel to match with the sift descriptor somewhere else, right? So it's kind of like a generic data term. But I will say that those kinds of things are not really well suited to the kinds of optical flow problems you encounter in visual effects. I mean, usually you're trying to estimate flow between things that are basically, reasonably well spaced apart images from video, not from images that are like from different perspectives. So a final thing is that, again, there's so much of a effort in computer vision to make things fully automatic, but there's really no reason why that has to be true. So there's a nice algorithm called basically human-assisted motion annotation. And this is by Liu et al. And so the idea behind that is the following. So basically, you have a video sequence, for example, where I want to estimate the flow. And so the right-hand algorithm may be the kind of result that you would get from applying a generic optical flow algorithm, where the colors here kind of represent the strength and so you can imagine the color basically represents, for example, the orientation of the flow vector, and the depth of the color represents how strong it is. It's hard to represent the flow field as a color map. But the point here is that, if you run a fully automatic algorithm, you may get a flow field that you don't like. Whereas you know that, for example, in this scene, I expect most of the pixels on this car to have one flow vector, and these guys, and the background should be different. So what this algorithm asks you to do is to provide a kind of a coarse user-assisted annotation of what are the foreground objects and what is the ordering of the foreground objects. And that does this kind of smooth this in layers idea to find the best flow fields it can, given the user constraints. And so, in the real world, that makes a lot of sense, right? Like, why do you kill yourself to have an automatic algorithm that gives you some weird result when it wouldn't take you that much effort to make a quick segmentation like this, where you kind of draw some boundaries around some rough objects and say, hey, algorithm, this is where I kind of expect the chunks of flow to be. Then the algorithm goes off and does the best it can with your prior information, right? So what I want you to do on the homework is basically like this, where I'm asking you to take 3 canned flow algorithms off the shelf, right? One is this Horn-Schunck algorithm. One is this algorithm, I guess I should say it here. So there's also this algorithm from Brown, Secrets of Optical Flow. Ooh. So basically, if you read this paper, you don't have to read the paper, but this kind of talks about what are the best practices for all these little modifications that I've been telling you about over the past 15 minutes to make a flow algorithm that really performs well. And they have a nice free implementation of what they consider to be kind of a best practices flow algorithm. And they also have a reference implementation of Horn-Schunck. And so what I want you to do is say, okay, take the reference implementation of Horn-Schunck on a couple images that you took yourself. How well does it do? Now take this, nice computer vision optical flow algorithm. How well does that do? And now try doing it with this motion annotation where you give the algorithm, you kind of show the algorithm, hey, these are the layers I think that you should have, and how well does that do, right? And so that's kind of what I want you to do over the homework, is to kind of fool around with some of these flow algorithms to see how well they look. And so, again, how do you tell how well it looks? Well, you can do some, clicking. You say, okay, well, what was the flow vector for this point in image 1? Does it point to the right place in image 2, right? You can visualize the quiver plots of how the flow looks. It's kind of hard to get a sense from the quiver plot of really how good the flow is, which is why I was suggesting that you kind of cherry pick some points in the image and see what those vectors look like and do they point to the right places. And just like with matting, there's this big effort for benchmarking optical flow data, optical flow algorithms, right? So now if you have a new optical flow algorithm, there are some, common benchmark data sets that have known optical flow fields that have been very carefully ground truthed, and then you submit your algorithm to to this thing, and there's this kind of constantly ranked list of what are the best flow algorithms. And so what you're seeing here, kind of like in pixels, what is like the error in the flow vectors between what the algorithm spits out and what the ground truth is, right? So these days there's like a zillion optical flow algorithms. You can see that this table has like many, many entries in it. And then there are kind of references to kind of a note about what is the way that the algorithm works, and where's a reference to where you can find that paper, right? And so, even here you can see there are a bunch of 2014, 2013 papers that are still being evaluated on flow, right? So, and hopefully when you write a paper, you want your algorithm to kind of come out on top of this thing. Otherwise, people are going to say, well, why don't they just use this other algorithm, right? So optical flow research is a pretty tough field to break into because there's been so much work in it, right? Last thing I want to say is, so why do people use optical flow in visual effects? Okay, so now that we know what optical flow is, a very common thing to want to use it for is what I would call retiming of a scene, right? So for example, optical flow in visual effects, one key thing is in retiming, right? So suppose that I have a camera that has a constant frame rate. So say this is, for example, a 60 frame per second camera. So I'm using this to record some faster than normal action, right? And now what I want to do is I want to slow this down to, say, 45 frames per second. And so how would I, so suppose my first image is the same, okay? So if I want to get 45 frames per second, then that's like saying that my next image has to be kind of somewhere between these two images, right? So kind of I want to get an image that is here, and maybe the image is here. And so how would I synthesize this image? I wouldn't just take this image or that image. What I would do is I would say, okay, I'm going to take the image I get here and the image I get here, and I'm going to combine them to form this new image. And how would I combine them? I would basically say, okay, one thing I could do is I could step, so say I wanted to make a halfway image. I could step halfway along the optical flow and produce the image that I would get. Or, even better would be to say, okay, I step halfway along the forward flow and halfway along the backward flow, and I average those two things to get that image, right, for example. So, in that way, what I'm doing is I'm kind of not stepping all the way along the full motion vector. I'm stepping only part of the way and putting the pixels down and making a new image that looks better, right? And so this kind of retiming happens very, very often in visual effects production, where you want to take some shot footage and make it appear to be a slightly different rate, right? So you can imagine that on the interface side, someone just basically has a knob that they're saying, okay, let's slow this down by 20%. That's really what's going on under the hood, is that you're fooling around with the optical flow vectors to synthesize these new images, right? Another kind of thing that maybe I don't need here. The other thing that happens a lot is warping texture, right? So, for example, suppose we want to do an in-painting problem where I have a guy that is occluding the background, and in the next frame he moves over to here, and suppose I want to remove him from this background. Well, what I would do is I would say, okay, if I knew, well, so this is a little bit of a combination of things, not just optical flow, but so if I knew kind of where the rest of the background was moving, and I observed this patch of pixels over here, I could flow it back to over to here if I kind of knew what the flow was locally, right? So I can kind of say I can estimate what the pixel flow is around where I want to put the texture back in, and then I can kind of push those flow vectors back over into the image to put down the texture in the right place, right? So this kind of, moving pixels around based on optical flow is also a very common thing to want to do, okay? So I think those are the two main reasons that you would want to do flow. And so it's actually a very useful thing to know where all these pixels in the image are moving, right? Okay. So that's like, again, the very high-level overview of optical flow. To really get into the mud of, how all these refinements and stuff work, a good place to start is with the Secrets of Optical Flow paper. That's a nice paper to read to learn, number one, what is the basic idea, and number two, what are all the little things that you should do to make your algorithm a little bit better. Okay, so any questions or comments?
So this rewarping texture idea, it seems to imply that you can kind of use like optical flow to kind of fill in like information that's missing.
Right, so I mean, optical flow is one way to attack the in-painting problem, right? So if you have lots of information from future frames, you can use optical flow to push stuff back into the holes, right? Yes, so that's definitely true. Okay, so go to